Hydrogen and iodine reactor form HI. So interestingly, there's the equation. They've got the same number of moles on each side. So it's one of those, 1-to-1 equilibria where changing the volume, the concentration, does not result in a position of equilibrium shift. It's just interesting to notice at this stage. You've also got an endothermic direction going forwards, exothermic going backwards, and they've given you a graph. So you can see that something happened at T2. It looks like the concentration of everything increased, and the only thing that can do that is changing the volume, decreasing the volume, bringing the particles closer together. The rates of reaction will increase in both directions, but remember there's no position of equilibrium change. So there's no sort of curve after that you would expect if you had a different number of moles on each side of the equation. Now, something happened here. We actually know that because the concentrations of everything doubled, then the volume must have halved at T2. Okay, and it's been re-equilibrated almost immediately afterwards. Which one is correct? A catalyst was added. No, that's wrong, because if a catalyst was added, the concentrations would stay static. When a catalyst is added to an equilibrium mixture at equilibrium, no change happens in the concentrations of anything. It's already at equilibrium. If it wasn't at equilibrium, it would reach equilibrium faster, but the rates will increase, but not the concentrations if a catalyst is added. The amount of HI is greater at T3 compared to T1. Well, amount refers to moles, the actual number of moles, which isn't changed by compressing it. And there was no position of equilibrium shift either, so we didn't change the number of moles just by compressing it, and there was no position of equilibrium shift changing the number of moles, the distribution of reactants and products. So no amount of reactants and products changed. It's not B either. Concentration changed, by the way. Right? So compressing it increased the concentration. Compressing it increased the rate. It doubled the concentration, it doubled the rate, but it did not change the amount at all. The rate of reaction producing HI is the same at T1 and T3. Now, we've already said that it doubled the rate, right? Because if you double the concentration, you double the rate of reaction. The rate of production at HI at T3 is double the rate of production of H2 at T3. Well, let's check. At T3, or indeed at any time, the production rate of H2 is half a mole per equation. The production rate of HI is 1 mole per equation. Therefore, D is correct. Now, question 28. One change was made at time T4, which altered the equilibrium constant. Okay, so to change the equilibrium constant, they must have changed temperature. If temperature went up, then K would have gone up as well, because it's endothermic. And you can logic this through, like if the temperature goes up, it'll proceed in the endothermic direction to partially offset the change that was made. So if temperature goes up, K goes up for an endothermic reaction like this one. If temperature goes down, then K goes down for an endothermic reaction like this one. Equilibrium was re-established at T5. The rate of the reverse reaction at time T5, a new equilibrium, was higher than at T3. So the only temperature change that increases rate is an increase in temperature. So it has to be an increase in temperature, and K would also have increased. So the equilibrium constant, therefore, has to have increased. The total chemical energy, that's interesting. Well, the amount of chemical energy in the system, this is very interesting. Let's do an enthalpy change diagram. We know it's endothermic, and you've made more product. So you've made more chemical energy, because H is chemical energy. Good question. The answer is A. More product. Let's just go through that one more time. You've got enthalpy on this chart. This is the shape of an endothermic reaction. By producing more product, you've created more molecules with a higher H, with a higher chemical energy, H being chemical energy. More product with a higher chemical energy is an increase in chemical energy.